Welcome to This Explainer. Today, we are diving into something absolutely fascinating: how mathematicians and AI are desperately trying to crack the ultimate code of sports outcomes. Whether you're just a casual fan checking the weekend's odds or a hardcore data scientist analyzing performance metrics, the holy grail of sports has literally always been forecasting the future. So we're going to trace the wild evolution of predictive models. We'll start out on the football pitch and eventually make our way over to the basketball hardwood, uncovering how we went from some pretty basic statistical distributions all the way to insanely complex deep learning neural networks. It's going to be a fun ride.
Here's our playbook for today. We'll kick things off with a quest for predictability, then look at Poisson goal modeling, and move into logistic regression. After that, we'll simulate whole seasons with Monte Carlo, dive deep into basketball AI, and finally, look at where these algorithms actually break down.
All right, part one, the quest for predictability. Let's talk about forecasting the chaos. Picture this. You're standing in a massive, packed stadium, right? You can actually feel the energy of the crowd vibrating in your chest. Now ask yourself, can math, just pure numbers, actually predict the total chaos that's about to unfold on that pitch? We all know the absolute beauty of sports lies in its randomness. But to answer if algorithms can actually see the future, we kind of have to strip away the emotion and just dive into the underlying data. Because while fans will spend hours at the pub debating who's going to win, and maybe even guessing the exact scoreline, there really is a hidden structure to all this unpredictability. Now, take a look at this brilliant quote from a KTH Royal Institute of Technology study. It hits the nail on the head. It mentions a stochastic element. That's just a fancy way of saying inherent randomness. And that randomness is exactly why data scientists are obsessed with building better, much more complex models to outsmart the chaos. Because of that wildcard element, well, it's pretty unreasonable to expect any model to give you absolute 100% perfect certainty. But that definitely doesn't mean we can't get incredibly close.
So let's get into part two, Poisson goal modeling. Let's predict some future goals.
Let's meet our very first mathematical scout on the field. When we're talking about events that happen seemingly randomly in a fixed time frame, like, say, goals in a standard 90-minute match, statisticians almost always turn to something called the Poisson distribution. Think of it like this. If you know a team averages exactly 2 goals a game, you feed the model that expected average. In math, they usually call this lambda. Once you feed it in, the formula spits out the exact percentage chance of that team scoring 0, 1, 2, or even 3 goals in their very next outing. Seeing it mapped out makes it so much clearer. By plotting out the probability curve for different expected goal averages, we essentially anchor that random feeling of a goal to hard math. Check out the blue line where our lambda, our average, is 0.5. The absolute highest probability there is scoring 0 goals, right? Makes sense. But then look at the red line where lambda is 3. The whole peak shifts dramatically, showing a way higher probability of scoring 2 or 3 goals. Honestly, this seemingly simple distribution is the literal bedrock of modern sports forecasting. Moving right along to part 3, logistic regression, going beyond just the goals. So just looking at goals, it really isn't enough to get the full picture. Researchers had to upgrade to a sort of tactical coach model to evaluate all the gritty, real-time details happening on the grass. Because a football match is about so much more than just the ball crossing the line, right? It's possession, it's aggression, it's field location. By feeding a binary logistic regression model with all these specific variables, corners, fouls, shots on target, those KTH researchers I mentioned earlier, they were able to correctly classify match results an astonishing 79.3% of the time. They took a massive data set of over 4,000 Premier League games, tracked 114 different variables for each one, and boiled it all down to see exactly what actually wins games. And here's one of the coolest takeaways. The data actually proves that playing in your own stadium, combined with keeping your shots on target, carries massive statistical weight. This model showed us that home advantage isn't just some psychological myth or just the crowd being loud. It is a heavily weighted coefficient in the math that physically tips the scales in a team's favor. Okay, part 4, Monte Carlo seasons. Time to simulate the future. What if we want to get really ambitious? What if we want to predict not just a single game, but an entire, grueling 38-game Premier League season? Predicting one match is tough, but calculating the cascading butterfly effect of a full season, that takes serious computational muscle. Think about when you're filling out your weekend brackets. Researchers at Lute University basically do that, but on steroids. They take those expected goals from our friend the Poisson distribution, simulate a single match, log the result, and then they ruthlessly repeat that exact process 100,000 times. This is what's known as a Monte Carlo simulation. By running the season over and over again, they account for all the crazy variance and randomness to find the absolute most mathematically probable final standings. And when the dust settles on those 100,000 parallel universes, you get something like this. This grid gives us a tangible, percentage-based probability of exactly where every single team is most likely to finish. For example, based on expected goals, the simulation could predict with super high confidence that a team, let's say Liverpool, is highly likely to finish right in the mix for that highly contested final Champions League spot. It takes the pure randomness of the Poisson distribution and scales it up into a shockingly accurate, season-long forecast. Next up, Part 5, Deep Learning Hoops. Let's bring AI into college basketball. All right, we are leaving the football pitch behind and heading over to analyze the incredibly complex dynamics of NCAA college basketball. And we're bringing in the big guns, artificial intelligence. While logistic regression and Poisson models are amazing, the sheer volume of sequential data in a massive basketball tournament really requires a model with a bit more neurological firepower. To predict this tournament, a deep learning model has to swallow an absolute ocean of data. Researchers engineer these clever features like ELO ratings, which is basically a system that measures relative team strength based on their past matchups, to give the AI a really nuanced view before the ball is even tipped. By layering in super granular box score stats, defensive rebounds, assists, steals, the AI manages to process all these complex, swirling relationships simultaneously. So when researchers actually tested these advanced neural networks against each other, they found a super fascinating split. The long short-term memory model, or LSTM, was way better at calculating the exact highly calibrated probability of a win. But the transformer model, it was actually superior at just bluntly picking the right winner. They figured this out using two different metrics. First, the Breyer score, which evaluates exactly how accurate the actual percentage predictions are. And second, the AUC, which just measures if the model can accurately rank the winner higher than the loser.
Looking at these two models side by side really brings it home. See how the LSTM on the left tightly hugs that perfect calibration line, that dotted line right through the middle? That proves it is incredibly reliable for exact odds. Meanwhile, the transformer on the right, it kind of wanders off the line a bit, but it shines when you just need raw ranking power. Think of it this way. If you're building a professional sports betting model and you need to know the exact mathematical probability to find an edge, you definitely want the LSTM. But if you just want to win your office bracket pool by accurately picking who advances to the next round, the transformer's raw discriminative power is absolutely your best friend.
Finally, Part 6, Algorithm Limits. What happens when the models break? Now, despite all this incredible computational firepower, we have to admit, the machines are not flawless crystal balls. It's so important to remember that no matter how advanced these models get, at the end of the day, they are still trying to quantify human behavior, and humans are notoriously messy. As researchers from Stanford noted when they applied machine learning to NBA games, these models can totally clash when faced with extreme outliers. A sudden, unexpected injury, or a heavily favored team just having a uniquely terrible night shooting the ball, the math can't handle it. Plus, algorithms really struggle with something called human transitivity. In basic math, if A is greater than B and B is greater than C, well, A must be greater than C. But in sports, absolutely not. Just because Team A beats Team B and Team B beats Team C, it doesn't guarantee Team A will crush Team C. Weird matchups, team psychology, and specific playstyles completely break those rigid mathematical rules. So I want to leave you with this final kind of philosophical thought. As our math and deep learning models keep edging closer and closer to perfectly forecasting the final whistle, does the true magic of sports actually lie in the beautiful fact that humans can still defy the data? I mean, we can simulate a season 100,000 times, and we can train a cutting-edge transformer model on decades of box scores. But the whole reason we still buy the tickets and tune in is for that 1 in a million outlier, that stochastic element. That's where the magic is. Thank you so much for joining me for this explainer, and honestly, I hope you never look at a scoreboard quite the same way again.